what you see here actually is not a constant movement, but behind the scenes it is constant actually. This is definitely related to counting. Like you see here, 1 rotates and 2 and so on. Let me show you how this can be related to counting, or how it is indirectly. Here we have 0, here we have 1, 2, 3, 4, 5, 6, and now we rest. The equation is on the left side, as you see, and obviously it has to do with the circle and the sine function, because it's sine function. You see here the movement. If we see behind the scenes what's going on, you see where the movement is constant. It is point B is actually the point that is moving everything. You see here on the left side, when I stop it, when I turn it on, it moves in a constant speed. If this is not very obvious, I'll stop it and hide this segment. Do you see it? It is rotating constantly. And this is definitely also related to Kepler's law. How? If you remember, we can pick a point. Let's say here, point E. Let me move it a bit and hide a few things. I'll hide this one. All right. And what we will do from point E, this one, we will make a circle. Let's say radius half. And we'll just repeat the steps that we've done last time. We'll make a perpendicular to AB at E. Then we connect A to this point, point F, which is the intersection, and then we make a parallel line to AF that passes through B. And now we take the perpendicular bisector of this segment. I'll just show you. This one, GA. We will take the perpendicular bisector of it, and we will see the intersection. It is H. It is H. Obviously, well, not exactly obviously, but H can trace to either a circle, an ellipse, or a hyperbola, or you will see when it will trace to a parabola, there is something very weird that I want to show you. First, let's show trace, and let's start moving. Point B. I did not show trace, sorry. I repeat. Where is point H? H, where is it? Yeah, now I see it. Show trace, and let's go. You see this one movement here? Does it remind you with what we saw with the cardioid? But this one is a more extreme case. I think. Look, let's compare all the cases. So if I bring it here, we will see a hyperbola. If I bring it a bit up, let's say here, for example, the curvature will be harder. If I bring it even closer, now let's take this extreme case. Do you see what's going on? I'll bring it even closer. Now we should get a bigger ellipse, or a wider one, lower eccentricity. If I do it like this, for example, it will be even lower. The closer I get it, the more circular it will be, until it becomes here absolutely circular. Give me a moment. Yes, I think here. Did I get it correctly? Almost 0.01, but I think you got the picture. So here we have a circle, here we have an ellipse on all the points here. And the ellipse gets higher and higher in eccentricity the more I draw it away. But you will notice that the case of a parabola, which is between an ellipse and a hyperbola, it should happen here. So as you see, what we get is a single point. I apologize, what did I do wrong? Oh, I made the circle bigger. Let me go back. Yeah. So you see that a parabola is actually just a single point. Now you're asking, wait, how does this make any sense? I will not. I myself can tell you what I think is happening. I don't know if you agree with me, but what I think is, you see this hyperbola. If you look at the upper side of it, it looks like if you connect it with the lower side here, you should get an ellipse actually. Um, it's like you are. It's like what you're doing is. Let me make an ellipse here on the side. I'll pick 2 points. All right. So it seems that in the case of the hyperbola is we are looking on this side and at this side. At this side, let's make it more higher eccentricity, even higher. All right, I think this is enough. You see here, well, in this case, we have here the lower side. And on the other case, on this case, we have this side. But an ellipse is also a circle, and a parabola. How can I say that? Anyways, let's go back to the topic. I don't want to get too philosophical about this. So let's go back to the cardioid. Actually, let's show it. All right. Do you see the connection here? Not here, but when I do it like this, to the Kepler law. If you imagine H is the planet, and A is the sun. Let's give it a bright color, orange one, green one, I don't know. Good enough. Here it is slow, and then voila. But I said about time, like how can this be related to time? Let me take a screenshot for later. This equation, it's simply what's saying is x, cosine x sine x. Let's stop this one to not get very confused. I will hide it. So this is simply sine x. The problem with it is we are taking these numbers for granted, 1, 2, 3, 4. We are taking counting as a simple thing, these equal distances. But it's actually not very simple. Let me hide it and show you what I mean. Here. No, it's good. And let me hide also the y-axis. When you look at this, you don't know where is the beginning and where is the end. But when you have an atom that emits light, it should have a beginning, right? Although we don't know if it has an end, or theoretically does not have an end, according to the laws that we know about physics. Einstein's, we are applying actually some classical mechanics in this case, that light moves endlessly unless it gets interrupted. An object will keep moving unless you have a force that changes its directions, or anyways. So I said it might be related to time or location at least. Well, time and location are related to each other, obviously. What we need is y equal x. Now when we have this, now we will have a beginning, actually. So when we have x sine x, we get this. But now you are wondering, wait, how can taking the cosine of that, or even the sine of it again, you can try both of them, or we can try it together, will bring us to counting. Look, when we zoom here, let me hide the other. These three functions that are combined into one. We have here 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4. Yes, correct. 6, 7, and so on. We need to ignore x for a moment and look at this, at these, at sine of x and cosine of x. So we actually need a fourth equation. Cosine x. I'll hide this one. These two actually, I'll stop here. I don't know how to continue. I need to think about it more. But yeah, this is the two-dimensional version of it. Let's just stop here.